Good morning, good afternoon, and good evening, everyone from all around the globe. My name is Eric Mail, and I'll be helping moderate today's webinar on machine learning with multi-GPU training. One of the most powerful features of JuliaHub is how it enables quick and easy access to high-performance GPUs to speed up your code with CUDA.jl. Combined with Julia's multi-threading and distributed capabilities, you can go even farther on JuliaHub by connecting to multiple GPUs simultaneously. In this webinar, we'll see how this can accelerate standard machine learning workflows for both supervised and reinforcement learning. We'd like to have an interactive session today, so please write your questions in the chat, and we'll either address them on the fly or address each question individually following the demonstration. With that said, I'd like to introduce you to today's presenter, Dr. Matt Bauman. Dr. Bauman is the Director of Applications Engineering at Julia Computing, obtained his PhD in bioengineering from the University of Pittsburgh, and is a longtime contributor to the Julia language. Please welcome Dr. Matt Bauman. Matt?
Thanks, Eric. Thanks, everyone, for joining us today. I'm really excited about this demo. I think it should be really cool and a lot of fun, and really is far and away the most complicated demo we've done on a live webinar yet. So hopefully everything works. It's a big task, and really that's what we're talking about when we talk about large-scale machine learning with potentially many GPUs all working together. We're talking about real compute resources and very large scale models. And so that's what makes this so exciting and what makes it really so powerful to be able to do this on JuliaHub. For those of you who may be just stumbling in here and aren't terribly familiar with the Julia programming language, I encourage you to check it out. That's not really what we're going to focus on in today's talk. We're really going to charge deep and straight ahead into machine learning with GPUs. But the long and the short of the Julia programming language is that it's fast and expressive, and that 1-2 punch enables applications like this. And yeah, as Eric says, I am happy to be interrupted as we go through this. You can either throw questions in the chat box. I have that open and try to keep an eye on that as I go through the demonstration. Or feel free to unmute yourselves as well and ask questions live. Most of today will be a live interactive demo where we have the system at my fingertips and we can play around, make changes, and see what happens. So please don't hesitate to ask questions, because it may be possible that I can try something out or dig into the question at that moment. It also may be that it's something that we'll address towards the end. So I'll keep some time towards the end to have a dedicated Q&A. So if we don't get to your question live, don't worry about it. We'll try to make sure that we come back to it towards the end, and Eric will help keep me honest on that point. So really, what we want to focus on today is JuliaHub, and for those of you who have been a part of these webinar series, hopefully, a lot of this seems familiar to you, right? These are kind of the main 4 pillars of JuliaHub for compute, where we talked about some of the interactive development features, which we'll be using incidentally throughout today's demo, but I'm not going to focus on them. If you're interested in finding more about them, you can find the webinar from last April on interactive development on JuliaHub. We're going to talk a lot more about the large-scale distributed compute model and how that interfaces with GPUs. But again, we kind of went over the basics here earlier this spring on how deployment of models and applications works. You can kind of check out those features later on. Importantly, this second webinar that we went over earlier this spring, it talked about how you can deploy interactive apps. Again, we'll kind of touch on that, but not go too deep. So if you're interested in finding out more, you can pull up that previous webinar. Professor Edelman came on last month and talked about kind of how you can structure and think about parallel computing with JuliaHub. had a really nice interactive session. You can find that as well. All of these are on our website. You can go to the resources tab and drill down into the webinars. These and many others you can find. And this webinar will appear there in a few weeks as well, once we've processed the recorded video and such. So check out those for the kind of the groundwork for the basics of sorts. And really, if you're not familiar with that, that's all right. Because today we're really going to dive into what these things look like with GPUs and with large out-of-core data. And so, the basics, we'll see how they work. And you're welcome to ask questions on them as they arise. But really, I want to dive in deep on the GPU demos and really spend most of the time today actually working with these demonstrations. So we have two different demonstrations that we'll do. The first that we'll cover is a reinforcement learning task using AlphaZero.jl. We'll see how you can use this open source package that's actually structured really nicely for distributed compute out of the box on JuliaHub and how you can play with it there. Then we'll, after we've looked at that example, we'll look at what it looks like to do distributed supervised image classifications using the kind of standard ImageNet data set. And importantly, the second demonstration we'll see how large data really plays into things and how you can really dig into large data sets directly on JuliaHub and the kind of power that gives you there. So when you're doing reinforcement learning, right, you're kind of playing games against yourself or training against yourself, and so you don't have a large data set. So it's kind of a different sort of structure as compared to when you're doing large supervised classifications. You can have, you by definition need lots of data. So of course, there are many other machine learning techniques that we won't be covering today, but these two kind of give a representative sampling of the sorts of techniques that you may be using and how these things work. So for AlphaZero, this is, the name may be familiar to some of you because it got quite a bit of popular press about 5 years ago when this was the training agent, or really the algorithm in some senses, that was able to learn the game of Go to the extent that it was able to beat the best human player in the world. Something that, even just 10 years ago was thought to be impossible. And it's largely impossible, or was thought to be impossible, or I should say it's hard, because, for the game of Go, you have huge, huge, huge tree searches, right? Where at every step along the way, we can replay this animation here just to kind of demonstrate, each step along the way, there are many possible moves that you can make. And the numbers just grow exponentially to the truest meaning of the word and just become completely uncomputable in some senses, right? You just can't do the traditional sorts of tree searches that have worked for other games in the past. And so AlphaZero is actually, I think the implementation from the 2016 tournament was AlphaGo. AlphaZero is a refinement of that implementation. That it's actually a simplification that works a little bit better. And the key insight here when you're doing these sorts of reinforcement learning tasks is that it's combining a tree search, combining looking through these trees of things with neural networks, where you have a network that kind of identifies which aspects of the tree seem to be positive to explore. And then you use the tree search to explore those limited regions. And AlphaZero is the framework that does that. And it works nicely with the game of Go. It also works nicely with other games as well. And so Jonathan Laurent at Carnegie Mellon University has created and put together this very impressive open source package called AlphaZero.jl that has these reinforcement learning techniques built into it entirely in pure Julia code. I think latest count it's somewhere between 2,000 and 3,000 lines of code, the core algorithm is. And so it's relatively simple. He sees this as not just a execution engine, but also as a learning tool to understand AlphaZero and kind of get a sense of what the core algorithms are doing. And so he takes a lot of care in the actual code itself and making sure that not only is it doing what it should be doing, but also that it's readable, understandable, and teachable. And so that is, I kind of represent that in this very cartoonish, simple bullet point here. But I think that undersells it really, and that the beauty is that it's entirely pure Julia and it's understandable, and you can play around with it yourself. At the same time, it's fast, right? And that's kind of the 1-2 punch of Julia itself, that it's a high-level expressive language that can implement fast algorithms. And as compared to other implementations of this algorithm, right? This is a very famous algorithm that lots of folks have implemented in lots of different languages. If you compare it to, say a Python implementation, or even, some of the harder C or C++ implementations, this holds its own. So on the order of 100-fold faster than the Python implementations, competitive with the C implementations that are hard to understand, right? They're hard to see. And what makes it really fun, though, is that it is extensible to other games. So like we said, the training agent for Go, that's a hard problem. And this network, this infrastructure works for Go, but it takes a really long time to train. And so one of the nice things that makes this understandable and easy to use is that, well, you can plug in different games here. So that's kind of the bullet point here, is that you can play around with different games. I believe tic-tac-toe and Connect 4 are implemented, and we can play with out of the box. We'll be looking at the Connect 4 games today. And then lastly, and most importantly, the algorithm itself is built to exploit distributed compute when it's available, and in particular, distributed compute on GPUs. So let's take a look at what this looks like, right? I can talk about this all day at a high level, but the fun part is, of course, to look at it and find it online and poke around with it. So let's go to JuliaHub.com here, and we can log in and take a look at what we will be doing and how we'll play with this. So on JuliaHub.com, after you log in, you're presented with kind of the entry point for your compute tasks. And this demo will be focused almost entirely on the IDE and using VS Code in the cloud. Now, I've already launched my IDE and already have this set up for myself, just to save ourselves a second worth of time here. If you're just playing along or want to poke around at this yourself, you can go in here and launch a Julia IDE. Mine says connect, but if you just log into JuliaHub.com, you'll see that it has, instead of a connect button here, it'll have a big blue launch button. And upon clicking that, you can choose how you want to launch your interactive application. And it's just going to start a single machine in the cloud that you could connect with a GPU, with and depending on how fancy of a GPU you want to use. And by default, we make sure that you have a time limit here, so that way you don't forget about your expensive GPU machine over Christmas break or something like that. So that's how you can start, bring up machines in the cloud. And really, this is the easiest way I have to gain access to a Julia session with a GPU attached to it. I don't have a GPU on my laptop here at home. And so this is really how we can make GPUs accessible to everyone. Well, still expensive, but it is easy to spin up and poke around for a little bit of time here. So that's how you can start this. I've already done that, so I'm just going to connect directly to this. And when I do that, that launches into my VS Code environment on the cloud. You can see here that we have a interactive editor here where I've actually already been working and playing around with this. And we can go in and narrow in on our AlphaZero task. I'm just going to grab a tab that I have open here that is set up for me and has the code that I need here. So that's, I'll bring that in from my other screen just to save ourselves a little bit of setup. So now I have JuliaHub up and running, and I have checked out here this AlphaZero project. Now I've made only one change to the AlphaZero project above and beyond, just going to AlphaZero.jl and grabbing the source code from github.com. The one change I've made here is in the scripts folder, I've added a JuliaHub script. And this is a really nice and simple way of talking about how to deploy AlphaZero on JuliaHub. So what are we doing? Well, we want to use distributed compute here. We want to be able to use not just a single GPU on this single machine that I've started up on the cloud, but I want to be able to use lots of machines all connected together to each other. And we'll be using the distributed standard library for that task. We'll want to use AlphaZero, right? So we have this set up to, run using AlphaZero, and you can see here that we have, loaded into our project. When I checked this out, we have the AlphaZero project set up here for us that has all the dependencies and such, and is set up for loading AlphaZero version 0.5. Now, the one change that I've made that may be slightly unfamiliar for those of you who are new to distributed compute on Julia is I have this special @everywhere macro that ensures that you can go through and run all of this code on all the machines that happen to be connected to the main running script. Right now, if I run using distributed here, oops, on the command prompt, not on the package prompt, you can see that right now I have workers. I just have this one worker connected to this, right? I'm not in a distributed paradigm right now in my interactive session. And that's kind of what you want for an interactive session. You don't want to have lots of GPUs burning away in the background. You just have this one worker. So I can use this one worker here to set this up and run this interactively and play around with it. And then once I'm ready to deploy it, I can bring up a cluster of many GPUs. And it's in that everywhere that I want to make sure that in that cluster, every worker has access to AlphaZero. So that's what this @everywhere is doing. Then the next parts are very standard AlphaZero code here. And you can go over to AlphaZero.jl and check out the documentation on how this looks and works and see how to run these games and such. And this is very similar to this. Here you can see this is in the documentation, the script of how to run a AlphaZero trainer. You can either do it at the command line, it has some interactive tools, or you can have a script that does this, and it's just these 4 lines of code. So how do they look in JuliaHub? Well, I just have those same 4 lines of code, right? I create my experiment. I've added a little bit of debugging using @info here, and I create a session that uses that experiment. I could potentially change that experiment in all sorts of different ways, change around its name, its parameters, how many iterations I want to run, and so on and so forth. I have a directory in which I want to save the results, and you can tune this. It's a eminently hackable sort of structure, And then to train, well, we just resume our session that we've created. We've not done anything with this session yet. We've just created it. The command here is resume bang to say, hey, let's start off wherever we started from. In this case, we're starting from scratch, but you could grab a existing session and continue to refine and train it and so on and so forth. So that's the language here of AlphaZero is to run this. And the only additional tweak that I've done is I say, hey, well, let's keep track of how long this took using the timed macro to grab out the amount of time that was done. So that is very straightforward. And you'll note that nowhere at the higher level here did I talk about doing anything in distributed compute. And that's because the AlphaZero package itself automatically detects how many threads there are, automatically detects how many GPUs, how many workers there are, and tries to exploit all of those to their greatest benefit. And now only some of the algorithm actually runs in distributed compute time, and you can dig into the source and see how that works out. So there's some limited returns in terms of how many workers I throw at this, right? Because some of the algorithm is necessarily single-threaded or single node. Others can be done in parallel. In this case, in the reinforcement learning case, the parallel section is that parallel play of all of the training the game, running the simulations, playing against yourself, and doing the reinforcement learning task. That is parallelizable, and that's where AlphaZero will use multiple threads to batch up a bunch of work to send to a GPU on as many workers as you have available to yourself. So you can see that there's not really any special sauce in terms of JuliaHub here in running this. The extra stuff at the end here now, this is where I talk a little bit back to JuliaHub and say, hey, let's structure this so that way, JuliaHub knows what the outputs are and how to display those for us. And so we have a little mini JSON format here that we save as an environment variable for to be able to, at a glance, look at the number of iterations we ran, the amount of time. You could add other flags here as well. So if you were interested in doing lots of different games, you could add a game flag here, and this is connect for, and I could grab that from the session itself if I was playing around with this, right? And we'll see what this looks like when we look at a submitted job. And then lastly, and most importantly, all of the work that AlphaZero does is saved in a sessions folder. And I want to store all those results and not throw them away after I've run them. And so I can tell JuliaHub that, hey, let's grab a results file here, be it the tarred up, we'll just use tar to zip up all together this entire directory of all the output of our model. So that way I can download it and work with it interactively. So this is the running of this. And I can run this locally on this one interactive machine, right? I could just say, hey, well, let's include scripts /juliahub.com or JuliaHub.jl, and it'll just run this script on this one interactive machine. It won't do any of the uploading, right? Because I'm just doing this interactively, but it'll run this and give me a session folder here locally that I can play with. But it only has access to one GPU. It only has access to this one machine. And while I'm doing that, I can't do any other interactive work here, right? If I ran that, I'd be kind of stuck waiting for a few hours for this to train on this one machine. So instead, I can click on JuliaHub, this JH icon here. It connects back in to JuliaHub.com. Automatically detects, hey, I see you're working on the scripts /JuliaHub.jl file here. Let's use that as the kind of entry point to run. Let's see, I need to clean up my working directory here. Just 1 second. Well, actually, we can see what happens. Well, yeah, let's do that. So currently in my directory here, I have the sessions that I forgot to delete. I'll delete those just so that way we can start from scratch. Sessions. Well, yeah, I know it's not empty. All right, let's just move it. Okay, so I just cleaned up my directory, and the reason I did that is because what this does is it sees that, all right, we are in the AlphaZero folder, right? That's kind of the environment that we're in, where the project and manifest live, that define this environment. And the way that submitting this job works is it actually identifies that. So let's go back to my file list here, right? We're in AlphaZero.jl, and we have all of these files here, the source files, we have the script, we have all the necessary things, as well as the project and manifest that define the dependencies. So we have all of this available to us. We want all of these to be available to us when we submit this, just as though it would work locally, right? Just as though I said, hey, let's run this. And so when I go to JuliaHub.com to submit this as a batch job, it'll automatically bundle up all of these results, or all of the things that are in the AlphaZero.jl directory, all that source. I misspoke there, not the results, but rather all the source material that is there. And we're somewhat opinionated about that, and say, hey, don't upload your data files as part of this. And so we have a limit of, I think it's about 100 megabytes or so to upload that, and the outputs end up being bigger than that. So that's why I removed them, because I don't need to upload old outputs to run my new script. I want to just upload the things that I did. So that's why I cleaned up my directory here. I should have done that before this webinar, but that's left over from testing to make sure that this all works. So now for the important part, let's start this as a distributed job. So when we launched our VS Code, it was just a single process, right? A single job that just is on a single machine. Now we want to use distributed compute. And importantly, we want to use distributed compute across machines that have GPUs attached to them. And let's use the beefier 8 vCPU machines with V100 GPUs. And the way to read this, right, this is kind of how you're defining your cluster. This is the cluster definition part. So, and this is meant to read like a sentence here, right? So we start a distributed job with GPUs attached to it. Each machine, or each node is the terminology that we use here. Each node is going to have 8 vCPUs, and each node is going to have a V100 GPU. So that's a NVIDIA, it's a little old now, but it's kind of one of the workhorses of GPU compute these days. And then we need to specify how we want our Julia processes allocated to this machine. So we can either have, use distributed compute here, where each machine will get, if I have one Julia process for each vCPU, well, that means that each machine will get 8 Julia processes booted up on it and connected through the distributed compute paradigm. And for distributed CPU jobs, that can be a very helpful mode of execution. But when I have only a single GPU on this node, and I want each Julia process to have access to that, it's often a lot easier to just say, hey, let's have one Julia process for each node. So now that one Julia process will have 8 threads and access to the one GPU on this node, right? And so this is kind of how we define each node of our distributed compute. And then we just say, well, now let's launch a certain number of nodes here. And this allows us then to kind of multiply this out, right? So I have 8 threads times, however many nodes I do gives us that many threads. And each node has one GPU, so however many nodes I have has that one GPU. Now, one thing to note here is that in Julia's distributed mechanism, the first node that spun up is your coordinating node, or the master node, that has that distributes all the work across to everybody. And so the number of workers that you get is kind of the number of nodes minus 1. So if I wanted to have 8 workers, I'd spin up 9 nodes and then start this job. And again, now is when you really want to make sure that your limit is set up here appropriately. I know that this should complete within a reasonable amount of time. I'll give myself some slop and hit start job. So that'll go in, bundle up all my source material, all the script, and then run this script as kind of the main driving script for this distributed batch job that can run asynchronously, and I can have potentially multiples of these running at a single time. You can see all the jobs that are running here in my job list directly on VS Code. You can see that I have my Julia editor here that we're actually working in, right? That's the editor. We see it. I also have a Pluto notebook running. We'll see that in the second demonstration. And I have a job that I submitted of AlphaZero earlier this morning that we can peek in on now. You can also see that last night I ran another AlphaZero.jl that successfully completed. But this is how you can look at your jobs and see what's going on as they're running. So this job is still starting up here. Hopefully it'll appear in just a second on my job list. Well, we'll see what happens. But we can go back to this one that is currently running, right, and peek in on it. So under this action menu, I can go in and look at the live logs, look at what is this job doing right now? And this brings up a log window where we can see what's happening. It takes just a moment to stream in here. But let's see if we can load. There we go. So it took just a moment to submit my job. Now you can see we have our successfully submitted job here. And you can see this, the output of the currently running AlphaZero task as well. So you can see how it's going through each iteration, running the training. Here you can go in and see, okay, this is my script that I was running, right? You can go back to JuliaHub.jl and see these are the info lines that I had set up: info, creating experiment, creating session. You can see those appear just directly here, right? Creating session, creating experiment. Here's that training info line. And using these info lines is nice because it automatically marks, where you were, and all this is very easy to see. And then all the other output appears here as well. So you can watch this progress go, see it, watch itself play, and so on and so forth. So that is running AlphaZero and the interactive logs as you go. We can go in to a job that had already completed and I show its completed logs, and that has the exact same interface here, the exact same way of looking at this. But oh, oops, looks like yeah, that's funny. There's some errors there as the logs are going. It actually successfully completed, and you can download the results. And again, those results there are this sessions folder that I declared as my results file. So when I did that, it says, okay, here is that results file. I can either open it directly, copy the path, or save it. Let's save it into my current working directory here in AlphaZero, this session here. And so now I have, back in my session, I copied my results, downloaded my results to my local directory. I'm gonna close these notifications, and I have this sessions.tar.gz. I can untar it here, extract and unzip my sessions folder. And then I have available to me this sessions folder that I can go in and interactively explore from that distributed compute that I did. So you can go in here, sessions, and see the, you can look at the plots of, say, the loss over time. And these are all just stored plots that were generated by the submitted job, right? Generated as we go. You can go in and see, what the percentage of won games. I could choose, to have run this for more iterations to improve the training or less, and kind of play with it. It's a lot of fun to do that, and you can see this interactively. But we can also just go in here and use AlphaZero. Let's see here, where is that? Yeah, you can use AlphaZero itself to explore this sessions folder. And by saying, hey, we have this sessions folder named Connect4 here, we can explore this. And it actually loads the trained parameters, tells me what it thinks is the best move, and you can play back and forth yourself. You can actually play against the computer without seeing the answers, or you can play as both red and blue here. This is the Connect4 board, as well as which move it thinks, which column it thinks is the best answer. For the first player, it's learned that the best answer is to go smack dab in the middle. And the second player, maybe you go on the left side, maybe you go on the right. It's 95, 97% sure. Let's follow the instructions here. And then you can see it's already learned the best mechanism for pulling a draw, essentially. It's Connect4 happens to be a solved game, but this isn't using the solved solution. It's using a strategy it found to just stack up one on top of each other. Just keep going on this fifth column, fill up column by column. That tends to be the strategy over and over and over again. And as you do this, you can see, it gets a little more interesting here, but you can follow along and see, yep, we're just stacking these columns. So this is the kind of the fun of playing around with this and seeing this go through. But this is all just using AlphaZero.jl with a very straightforward iteration on the script itself. And I can go back to that script. There's a question in the chat asking if this would be available online. And really, I think we should make this available as a tutorial on JuliaHub help, but it's not much more than what's already documented in the in AlphaZero's repository. So yeah, we'll make this available as a tutorial, but this is pretty straightforward. So that is AlphaZero. Any questions on how we've been running this before I dive into the briefly look at the supervised learning example? I ended up spending more time here than I expected, but hopefully this was entertaining to see how you can work with AlphaZero. There's a question asking, doing this on an iPad. I think that this is just a web browser. I've not tried this on an iPad, but as you spin this up, it's not terribly different from Google Colab, right, where it has a web-based interface. And I think you should be able to. That it might be a little awkward. I've not tried that myself, but yeah. And at the moment, the way in which we've been using JuliaHub and the first class environment, we are 100% VS Code at this moment. You can spin up applications like this. You can also connect a local VS Code to JuliaHub. And I think, as time goes on, we may extend out that we do, back this with a full API. And so, as time goes on and as we make that API more and more public, hopefully we'll have more and more plugins for other editors as well. So with that, let's jump over to our other demonstration, which is ImageNet. ImageNet is a huge corpus of images that, of which some are labeled that allows you to do large-scale supervised image recognition learning using ResNets, residual networks and such. And this allows you to do this. And we'll be working on cleaning this example up. This example is currently still under development, but couldn't resist showing this off as well. But we'll be making this example public probably a little bit later on. The real benefit here of doing this on JuliaHub is that we have this one code base that runs everywhere, runs on your laptop, runs on a single node, potentially with either one or multiple GPUs on that single machine, or on JuliaHub Cloud. Well, that's the last part that we'll look at. And we're using the standard subset of the ImageNet database, which is 560,000 high-resolution labeled images of many resolutions. And this is where we start talking about data, right? Where we have all these images, we need them to be stored somewhere. And since we're using AWS as the compute backend for JuliaHub, the best place to put this is indeed directly on an S3 bucket. Now, because we're in Julia and because we have direct access and because we have this in a really nice standardized workflow, well, we have a nice way of grabbing out that bucket, working within that bucket, and kind of exposing that S3 bucket almost like a file system to Julia itself, using first-class APIs from datasets.jl. And so, we can upload these to JuliaHub, name our dataset, and we'll see what that looks like, and then asynchronously train this on, potentially many nodes, and play around with them live in reactive notebooks. So that's where we'll go. That's what we'll look at. And the code here is more complicated than the AlphaZero. This is more on the implementation side of things. With AlphaZero.jl, we were using a published algorithm, a published open source library, and just throwing that at JuliaHub. Here, in this case, we've done the implementation ourselves. We've gone in and built out this. This is largely work done by Daria Gandhi, who has done a lot of iteration, a lot of work on this, and I'm standing on his shoulders and demonstrating that today, where we have kind of a driver script that leans on batching these together, running each kind of mini batch across lots of GPUs, either on a single machine or on JuliaHub, and trains them and again, saves the outputs. So this is kind of the main driving script here. There are a few points that I want to talk about before we dive into the code, because it's going to be important. The one is that, this is how we open and iterate over our data set here. So we have a named data set with a name here that we open it with a little bit of a funny syntax here. It's called a blob tree. This is datasets lingo for just saying, hey, this is a directory of lots of blobs, lots of files. And so we open it as a directory, and we take that and do the data tree, right? This is the data of all the data that is available to us. And this is where having this first-class datasets API is really nice, is that we can subset this S3 bucket by a given path and say, okay, let's take our data. This is the path to the training subset that we want to use. And that is how we can set up our training data. And then we can have another path for the testing data and so on and so forth. But this is how these training data work. So then, again, we do the exact same thing where we come out with a final model. We save that. In this case, we'll just save a single file instead of a directory that Jonathan's put together that has all of the plots and such. Here, let's just save the weights of the model using BSON to do so. And it's just a single file, so we don't need to zip things up. We just say, hey, let's save this model in our current working directory, and then set that file as our results file. So that is using ResNet. Let's dive in and see what that looks like on JuliaHub. So again, I have this already open in another window here. I'll just grab this and bring it into this one. So here I have, again, my file editor is open and running on this ResNet demo, and this is what is this code we aren't quite ready to share publicly. I can poke at it. It's not private. I just mean that we've not cleaned up the repository to the extent that we're happy with it to make it a public repo. But here, just like before, we have a kind of a main, in this case, we called it a bin folder that has all of our scripts that does this kind of the main input, the main structure of our code. And again, we kind of have the package set up here like a package, right? Where we have a project and manifest set up to work like a package with a source folder. And this package is called ResNet ImageNet. And we, again, use distributed to load all the things we need. In this case, we're using Flux and CUDA directly to do the work that we need to do. And we call this driver function with a given number of cycles and epochs and batch sizes, and these things can be tuned and such depending upon the capabilities of your system and how deeply you want to train this thing. But now here's the magic, right? This is what I was talking about, the ImageNet data set. Where does that live and how does that work? Well, that is back on JuliaHub.com. And under JuliaHub.com, if I make my screen a little bit bigger, go into the compute menu, you can see that there's a data sets tab. And under here is all the data sets that I've played with. And in particular, here is this ImageNet data set that has 156 gigabytes here available to me to use. And I've tagged it, I've added a little bit of a description. Which actually lost its description. But yeah, you can see here, you can add descriptions to these, and you can see that this is how it's stored. It happens to be in an S3 bucket, and that's how I uploaded it. And so that is how this data works. And you can see that there's some storage cost here, but it's not much, and this allows you to do that. So by having a named data set here, that means that in my code, I can go in and, well, let's go in here and start a REPL. I should have done this ahead of time. We'll see how much pre-compilation I need to do. You can see that I'm already in my ResNet ImageNet package environment here. So that's in good shape. I can just say using data sets and then bring in the ImageNet data set here. So let's see if we can do that live. One of the really nice things about using this as a named data set is that this is, kind of agnostic as to where I run. And we're still working on completing out that story to laptops. But the goal here is that, just by having a named data set and by being connected to JuliaHub, we can look at that and grab it and lazily download it to whatever machine you have, right? So remember, this is a 150 some gigabyte data set, and I guess it's capitals now. I've been playing with this a number of times, and so here you can see, this is the description of it, and it knows where it lives, how you should work with it. And we can go in here and we can go in here and open this data set as a blob tree. And that'll take just a second to, essentially what it's doing here is it's listing all of the contents of that data set, and we'll expose them like a lazy list that I can arbitrarily load portions from by indexing into it with paths, which is pretty cool. So there we go. So here you can see we end up with a data tree. Here's that iOS VRC folder, and I can dig into this, right, as we go through. So this is how you can, it kind of looks like a file system, right? You can see folders and files, arbitrary things here. They can be whatever file system you want, and then you just open it with whatever if it's a CSV, well, you open it with CSV.jl. If it's in images, you can use ImageMagick like JPEG or something. So all of this is just really integrates really nicely with the Julia ecosystem. Let's jump to the chase here, right? So again, we want to train this. Again, we want to connect to JuliaHub. This will take just a moment to authenticate. We'll start again a distributed GPU job with a bunch of workers. I've already done this. I've already run this a few times. I don't know that we need to start this job yet another time. To look at it, we can go in to JuliaHub.com and go to my job list. Here you can see all these jobs that are currently running. And here's this completed ResNet demo. This is the same job list that appears in VS Code, just a different way of looking at it. One of the nice things that's available here is the ability to look at details. And here you can see this is that JSON file, that JSON outputs that I was talking about, that little JSON thing you can play with. So you can see how many cycles, how big the batch size was, the number of epochs, the number of workers, the number of GPUs that we ran on, and how long it took, how much it cost, and so on and so forth. So this is a nice, little bit more real estate to explore these, the outputs here. So I could, again, remember I saved these results as a BSON that I could download here, just directly in my browser. It'll go out, grab them, download it. It's about 100 megabytes of weights that it'll download. So I can download that locally to my computer, play with it here locally. Or I could go back to JuliaHub applications and launch a CUDA.jl notebook. And again, if you've not launched your notebook yet, this would say launch instead. And in this case, I don't need a GPU. I'm going to use Pluto to introspect the job, and so I can launch a CPU job here that's a little cheaper. And I'll grab a tab here that I have open. Let's see, where is that? There it is. So grab a tab that I have open that does this and goes in and looks at all of the jobs that I've run and am running. You can see I use the JuliaHub API here to give me a table, kind of like the table that we have before. And then when I select which job I want to use, it'll download that model, and you can see the exact definition of the model here. Now, where this gets really fun is I can, in Pluto Notebook, enable my webcam, take a picture, and that picture appears here directly, and we immediately run our machine learning model against that input. And so here you can see that it thinks I'm currently a Pomeranian. I could take a different picture, right? And the weights change just dynamically, reactively. These things change and play around with it. So of course there's no mat label in this data set, and the training here, we're continuing on working on making this train a little bit better, but this is the output that we see, and a really fun way of introspecting your outputs. So I think we're coming to the end. I want to leave at least 5 minutes here for Q&A, but hopefully this is entertaining and helpful and useful to you all to see how you can submit large-scale jobs, and we can potentially in the Q&A session look a little bit more into how the ResNet demo does its distributed compute, if anyone's interested in that. But I want to make sure that I cover any other questions before we go too deep into the code. One question that we had as I was going through that is if we had benchmarks comparing this across other things. That's not something that we've put together at Julia Computing yet, but it is something that I believe Jonathan has indeed done here. Let's see if there's the benchmark is benchmarking of the games themselves. Yeah, I don't know that. Yeah, I'm not sure if there are benchmarks here. I know Jonathan has done some benchmarking. I've not done that myself for AlphaZero. For ResNet, we're still working on optimizing that. We're not quite in the place to feel happy with the algorithm in terms of its benchmark performance. But yeah, I think the idea here is the capability. And yeah, you'll have to trust me that these are efficient algorithms. We are leaning on CUDA.jl to do a large portion of the code generation on GPUs and doing that. And that stack has far and away become very capable in the last year, 2 years. That is a really awesome way of doing GPU programming and continues to improve. And that's where we've done more of the benchmarking at the lower level, but we do need to get, make these demonstrations a little bit, benchmarked against a ground truth.
Real quick along those lines, I think there's another mention from Gustavo that talks about comparing the benchmarks between Python and C++. For something like AlphaZero, would you be able to wholly code something solely in one language and be able to make that comparison benchmark, or is Julia truly solving the two language problem by doing it all in one?
There are existing AlphaZero implementations that are purely in Python, but in discussions with Jonathan and others, they are abysmally slow. And so it is possible to do that, but it's just not practical. And yet, Julia is definitely the go-to solution there for having a single language that is fast and efficient. Whereas the other, there are other Python packages that are just thin wrappers around C code, right? That would be comparable performance, I would expect. But then they're far less hackable, far less understandable, and far less, usable. And importantly, one of the things that I think Julia really does extraordinarily well here is the capability of automatically using all the resources that are available to you. Right. We have worked with Jonathan some on AlphaZero, but really, this is all generic code that he's set up on his GPUs and such, and on some machines, and it's all generically written to use the resources that are available to you. And that's something that very few other languages have the capability of doing, where you can, run the same code base on a single machine, on, a single machine with multiple GPUs, with arbitrary numbers of threads, with arbitrary numbers of workers connected to it, and be able to exploit all those resources that are available to you.
There were a couple other mentions from earlier on. I don't know if you actually touched upon those directly or not, but is there an environment similar to Google Colab for Python, et cetera, to be used on an iPad?
Yeah, I think we talked about that largely. Yeah, I think we addressed those. It would be interesting to hear. We'd be very happy to hear reports on how this looks on an iPad, and if it is usable in some senses to play with this. The user interface here is really geared towards mouse and keyboard. So I'd be curious how this looks and feels on an iPad. It's not something that I've tried. Or, definitely not our first target. But yeah, if you try it out, please let us know how it goes. We have a public repository for all the issues and requests and such for JuliaHub that you can take a look at and see. Your input here is part of what makes this system so great.
So I don't see any other questions coming in. I think since we're at the top of the hour, we're going to call it a wrap, if that's okay, Matt.
That sounds great.
I do want to thank everyone for their participation. Thank you, Matt, for your time and the excellent presentation today. For the recorded versions of this presentation and our past webinars, you can visit the resources tab at juliacomputing.com. For any help with your existing Julia use case or upcoming Julia GPU project, please reach out to us at sales@juliacomputing.com, we'll be more than happy to help. Thanks again, everyone, and have a great remainder of your week.